nella chat.
Sì, sì, l'ho già messo sul sito. Ok.
Scusate, queste slide sono sul sito, queste che fate vedere?
Queste sì, le possiamo inserire sul sito se vi interessa.
Sì, può essere utile per avere un promemoria anche del
Certo, sì, sì, sì.
Giusto.
Sì, l'ho già messo sul sito. Ok, un minuto e partiamo. Okay. So my name is Francesco Marmo, and I will chair the second session of our workshop. And I just want to recall all participants to use the meeting chat to ask to talk, and I will give them the possibility to ask questions to lecturers after they end their presentation. So the first session, first lecture is a keynote lecture by Professor Maurizio Brocato. Professor Brocato teaches the École Nationale Supérieure d'Architecture. I'm sorry for the English, for the French pronunciation, ENSA, in Paris-Malaquais, and at École des Ponts Paris Tech. He is the director of the ENSA Paris-Malaquais Geometry Structure Architecture Laboratory, and he is president of the Department of Digital Matters in the same school. His research is focused on the interaction between shape and composition of structures, with particular emphasis to discontinuous and entangled systems. Today, Professor Brocato will give us a lecture on an all-time challenge for designers and builders of vaults made of monolithic blocks. He will show how stereotomy, which is the art of stone cutting, can play a fundamental and complex role in the statics of these structures. The title of his presentation is Stereoplexi, and I guess he can explain better than me what this word means. Welcome, Professor Brocato, the floor is yours.
Thank you very much. Thank you, first of all, for inviting me, and then also for letting us share this very nice moment today. So yes, the title of my talk is Stereoplexi, and I will take most of the time of the talk to explain why I choose this title. And I like, first of all, so I'll show some pictures and then tell a little bit about the mechanics, that is what I understand of those structures. Now, first of all, as a forward, I will start with a word of Professor Majewski this morning. There, a stone has three meanings. It was mentioning something that is that I try to summarize also in a few slides. That the stone, the design of the stone is at the same time the design of the wall. So it contains the overall geometry. It is the design of the statics of the system, and it is also an artistic matter in the sense that all those shapes contribute to the beauty of the building, not only to its statics. So in a sense, this is at the same time the heritage and the burden of what we name stereotomy. Stereotomy was a discipline born after the Renaissance, mainly in France and Spain, and as the definition is the art of cutting stones, so that each individual stone contribute to the assembly and make the wall a structure. Now, the motivation in the origin was simply to provide proper geometric rules for the assembly. And then, as the understanding of the structures of that period was based on two simple tools, that were the inclined plane and the inverted catenary, then the stereotomy became also, and in this sense I say a burden, became also a monopoly on the way to watch stone structures, that is the inverted chain rule. What is important in stereotomy is that it anticipated the idea that information can flow continuously from the detail to the wall and back, and that from fabrication to assembly. So in this sense, the sentence of Professor Majewski, a stone has three meanings, is what is important to us in stereotomy. On the other way, the fact that, that the law of inverted chain became a sort of law to be respected by all stone structure. This is something I would like to pass on, in a sense, to go beyond this sentence. So this is why I say, instead of watching at the cutting issue, let us talk of the weaving issue. And so stereotomy became stereoplexi. Plexi is the Greek word for weaving. I will start with a gallery because I think it's easier for you to understand what I'm talking about. This is a stone dome we built in Qatar, 6 meters span. It's a geodesic dome with a kind of particular assembly. I will talk about as Abbey design of dome. So this is one example. This is another example of interlocking domes, much smaller. Its presentation was done in Salon du Louvre in Paris, just 1 meter span, but it's built with the same technique. This is a saddle vault, a Bohemian saddle. So in my knowledge, maybe the first and the only so far stone structures that does not have a synclastic shape, an anticlastic shape. And those are built with the same techniques as walls that could be transported, lifted, and that can work under wind and other loads. So again, you understand that the multiplicity of loading that can be withstood by those structures testify for the fact that they are not only or simply inverted catenary systems. Here is again interlocked wall makes this time with cubes. It's a very old known assembly of cubes that can be found in treatises of the 17th century also, but that has been recently studied extensively for the high resiliency that the system can have under impact, especially. And now another dome. This time it is a gyroid shape, and the interlocking is made by following a Chebyshev net on the wall. This is on the dome. Sorry, this is a 9 meter span. Was built in Jericho in Palestine. Here are some details, and this is from below. This is experiences on carved joints. This is the dry stack tower that was built in Victoria and Albert Museum in London, and then rebuilt in an exposition in Dubai. And in the end, it is today in the Crimson Valley between Jerusalem and Bethlehem. Very famous at the time of this exposition because of the Friday prayers that were made there. Those are the two architects that conceived the tower, Yosef and Elias Anastas, in Victoria and Albert Museum. Some more and different work on stone. This is a sawtooth beam where a single bar make the system work as a beam. You can see that the end has no thrust. The bar is not a simple tie, but is bonded to the stone. So the system works rather like a concrete, reinforced concrete beam that like an arch with the annihilated tension. And following this path and some experiences that we made after, this is the anti-seismic structure, a 6x6 building built in French territory in Israel, the Benedictine Abbey of Abu Ghosh. And the roof is made with what is called a bay vault, which I will explain a little later. and it is reinforced with steel, and the columns are also only stone and steel, and the whole system is compliant to the Italian code. Notice that Palestine doesn't have its own code for seismic rules. So this is the outside of the same building. And going to the working of ties or reinforcement bars into those structures, this is a Monge helicoid, so it's a real surface with separate blocks. Unfortunately, those are not stones but concrete. This is rather a sort of an exception in my talk, but what is important here is that you have those complex joints that are linked with bars. And here, the last structure I want to show is a bench that was given to, taken by Victoria and Albert Museum as a permanent collection. And here it is, the place you find it in the museum if you go there since 2019, last February actually. February 2019, sorry. So now that I've shown some pictures, I can tell you why I think the inverted catenary system or thought is too much a limitation for them. This is the originally drawing from Fraisier that show the invention of Joseph Abbé at the end of the 17th century. You can see here this particular kind of assembly, and here are some tests. Maybe very few structures were built in the 19th century, only 2 actually in Spain with this system. And then at the beginning of the year 2000, some experiments were started in my school before I arrived actually. And so if we do some limit analysis on those structures, you resume here what you do. You assume, of course, you know the equilibrium configuration. Stones are rigid and bodies and are of infinite resistance. Joints are unilateral, and the forces that are transmitted through them are contained in some bounded convex domain. The load is given, and then you work on the reactions that becomes the parameters, so as to find a kind of a set of equilibrium forces, internal forces that withstand the external load. And if you find one system of of this kind, then you say that the valve is stable, and you can in most cases, of course, the system is a little more complex, but in the end, you get out with a kind of inverted fishnet. And so this network of truss lines became a paradigm to understand the structure. Now, I want to show what happens with usual flat valves, so not Abbé valves. So this is a barrel valve. Those are taken from Rondelet. This is a barrel valve. This is those are domes, and this is a cross barrel valve. And so in all those cases, you have these red lines that show how the loading goes to the supports. The red lines are orthogonal to the main truss, let's say. So those valves can be named after the shape of the Dupin indicatrice of their fishnet, in a sense, and they can be talked as parabolic or elliptic. Now, in the sense that here you have an elliptic shape or a parabolic shape that represent the inverted chain of the system. Now, if you look at Abbé valves, this is not so. So this is the example of the fishnet or the truss network for an elliptic flat valve. So, well, something that you can well understand with the truss, which is higher or lower, and you have this shape that appear. But if you do that with a Abbé valve, that you cannot use a single net. You must use 2 nets linked with struts. So you understand that the struts that are compressed items in the net represent the tension in the stones. And here I have some to the 3D. I wanted to have an animation, but it didn't work. So I put just some image from that. You see the struts are red. This is compression in the inverted system. So it is tension in the real system. And you see the blue nets that interweave each other that represent the compression in the stones. Second particular issue that is proper of Abbey system is that they can withstand inversion of the load. So this is typical pattern of self-weight against thrust. And you can see classical valves, of course, you can only have positive self-weight, and Abbey valves where you can have negative self-weight. So they can work in both sides, in both ways. This is why you can do walls with them. Now, if we go a little further and we try to understand what happens in mechanics, so how does it work, then you can assume blocks be anisotropic elastic bodies. You can have particular more Coulomb law on the joints, and do a step-by-step computation, like you can see here, the simulation of a 13th century flat arch in Beauvais. And what happens is that if you look at the stones and you try to look at the quotas of elastic energy, so you assume a stone with kind of a beam, and you see the elastic energy that is in the stone due to the bending moment, as due to the shear forces, as due to the normal force, and etc. You see that the highest, much higher than the other quota of elastic energy is in bending. So stones actually work in those systems as bended items, not as struts. So the inverted catenary system, if it tells something that is not really connected with the real elastic energy that is present in the system. And this is something else that you can see if you lock all the contact on the left, and if you leave the contact being possibly open on the right, you see how the elastic energy locates in the structure, rather in the center, in the case of a simple elastic grid without joints, or on the boundary, in the case of an elastic grid with opening joints. This is what happens. So in reality, when the different loading condition happens, when, for instance, this is the rising condition, transportation forces orthogonal to the plane. This is wind or horizontal forces on the panel, and this is vertical forces on the panel. You can see that, of course, the panel is able to react in many different ways. And so it is an element that can be a part of a structure much more complete in a sense than a simple valve. And for the case of domes, I want to show another couple of pictures where you have here all the joints, and you see some of them that are open, some that remain closed. So you understand that there is actually a pattern of opening and closing joint that makes the system work. And when you look at stone by stone, you can see that each stone has, this is von Mises stresses in the stone, and you can see that the stone is basically bended. This is to understand also the effect of flexibility, so the difference between a model with rigid blocks and a model with elastic blocks. Lighter colors represent rigid blocks, and blue darker colors represent flexible blocks. Those are computation made on a sawtooth loading on the previously shown dome, this one, and you can, and this is the top deflection, and you can see that there is a neat difference between assuming that the stone are not flexible and considering them flexible. This is, my understanding, this is because, of course, this is a statically undeterminate system, and the way that loads go to the boundary depends on the flexibility, and it cannot be, let's say, this dependence cannot be in general not considered. Okay, so I think I used the time, so I go to the conclusion that is a simple picture and the sentence of Auguste Perret: architecture is what makes nice ruins. And those are the name of the co-authors of the work that I've shown. Thank you for your attention.
Okay, thank you, Professor Brocato. So it seems very interesting, this work, because it seems you are building some walls that are actually flat, but we know that flat walls are have a very high thrust on the supports, while for what I understood, this kind of walls is working more in the flexural behavior. And so then how is this influencing the thrust on the support?
Yes, there is a, in considering thanks to the shape, the thrust on the support is much reduced. And we have made some analysis to understand how the shape of the blocks could affect the thrust, and if there is such an effect. If you read the treatise of the 17th, 18th century, there is a long debate about the wedge effect and the catenary effect, which one is dominant, for instance, in a flat arch. And actually, you understand that there was something missing in their reflection. That is, they were missing the knowledge of mechanics of elasticity, which wasn't there. This is a bubble diagram that shows compared computations on.
We cannot see the diagram.
Oh, I'm sorry. Sure.
Because you're sharing. Yes,
yeah, I'm sharing not the screen, but one document.
Okay.
So, okay, now I think you see the diagram.
Okay,
and
thank you.
So this is a set of different instances of the same vault with two parameters, and an angle. Alpha angle is what we call the splice angle, that is the shape of the stone, and the phi angle is the angle that allows how to be the inexorate, the shape actually of the frame. And well, the color, the gray or white, depends on the computation. This is rather a numerical issue. But what you can see is that this is the maximum thrust at one stone on the boundary, and you can see that it doesn't change a lot from one end to the other of the diagram. That means that actually there is not an enormous effect of the angle. As soon as there is an angle, in a sense, a reasonable angle, because of course you cannot do too much tight angles in stones, because then they break. So when you are in the range of angle that you are supposed to be able to build, actually, then there is not an important effect. The thrust is anyway reduced, and there is not a very important change in the thrust by changing this angle.
Okay, thank you. Just another question, if there are not from, yes, I give the priority to Stefano, which wants to ask us question.
Thank you, Maurizio.
Thank you.
Very interesting. I didn't know anything about this kind of flat bolts before. I was wondering if, I was thinking about the behavior of an arch, in which you have the bending effect with respect to the truss is also is dependent on the span to the 8 ratio. Is that in this kind of structures a geometric ratio that regulates the effect of the bending stiffness with respect to the, let's say, axial or membrane stiffness? If you see it in the large of the 2D structure, that regulates the behavior of the structure, that is from a bolt to a plate or something like this. I don't know if the question is clear.
Yes, clear. And we actually did a parametric study on flat valves to understand when they behave as vault and when they behave as what we can say, I don't know, flat valves of the Abbey kind. And this is one part of the answer is displayed by this computation. You can see that whatever this is, the parameters here, the phi parameters is again the splice angle. You pass from one flat valve like this to one like this, and you can see that there is always a dominance of bending. in a sense, I must say that when bending takes place in a structure, then it dominates. This is a little bit the reason why what Professor Moyevich was saying this morning, you get two words that are easy to understand and something in between that is more confused in a sense. Well, this something in between which is more confused dominates as soon as possible the other two. So to be a pure catenary in a sense is difficult. To be something in between, it's more natural. And so you see that in the end, as soon as you authorize by the splice angle or authorize bending to appear, then it dominates. And another question about geometry can be shown in this picture, maybe, yeah, this one. This is the equivalent of the fishnet for the Abbey vault. You can see that you cannot think of a single fishnet. So like this is a standard parabol elliptic flat vault. So you can imagine this inverted fishnet, and it's quite, I mean, intuitive today for engineering and architect to understand that. So it's a single net of forces. And here you need to consider two nets because you have phases, contact phases that actually cross each other in direction. And so the forces that are basically orthogonal to the face, or at least within a certain angle to them, they go down or they go up, depending on the direction you impose to the face, and not depending on nature in a sense. I mean, you force nature to do that. This is why I like so much this sentence this morning. In a stone, there is three things. Yeah, you actually, by choosing the shape of the stone, you modify the behavior of the wall system. And so then this geometric ratio is in a sense rather in the local stuff. Is it here? Is there geometric? You see here the line of thrust. It's out of the vault, but the resultant is in the joint. So this is a force passing from one block to the other. It is in the joint, so this is stable. But then it is equilibrated with another force which is there, which is in the other joint, stable also. And the two of them have a resultant that is out of the thickness of the vault. So this is why you cannot think the vault as an inverted catenary, because if you do so, then you have to assume to have a kind of virtual thickness that is higher than the real one because of the wedge effect.
Thank you. Very
I
interesting.
hope it's clear, but well.
Okay, thank you, Professor Bracato. Unfortunately, we are short of time, so we have to proceed with the session. And so Professor Pizzigoni kindly asked us to show his video. So I asked Andrea to share the video, and then we will proceed with the question and answer.
Very near to the studies of Maurizio Brocato.
Give me a second, I'm sharing the video.
Actually, the presentation by Professor Pizzigoni is very much connected to what Professor Brocato already showed us.
All right.
A new
Are you seeing this?
arise from the work of the French architects.
Yes, okay.
15th centuries.
The audio is good.
In 1739, in Paris, Amédée Fraisier published the Treatise on Stereometry. In the fourth volume, he shows some structures that he calls flat vault, like the one we can still admire in the town council in Arles. Their prominent features lie in the ashlar that build up the vault. They can be said self-stabilizing, and their specific shape made possible a self-balance property. Their static behavior is the most similar to the one of a three-dimensional flat bow, conceptually comparable to an herringbone of Brunelleschi. Today, the theory of Jacques Heyman and Santiago Huerta's studies let us understand the requirement for the balance in such kind of structures. Their theory gives us the tools for the crash kinetic and the safety bounds. Geometry, shapes, and balance constraints are defined from funicular trajectories of fluids and from thrust lines and surfaces. Such flat vault from French Baroque architecture derive from the same static principle we can find and document on the vault of San Gallo in Montefiascone and on the arches of Simon Mago and San Basilio in St. Peter's Cathedral in Vatican City. Those vaults from 16th century became the subjects of our research, mostly because of the lack of the plaster layer in the inner side, making the scan of every single brick possible and more easy. Such way, we were able to understand constructive motivation for position and displacement of bricks following herringbone shapes and losodromic spiral. It is meaningful in such respect the paper recently published by Vittorio Paris, Sigrid Adriansen, and myself in the last issues of Engineer Structures. Great attention to the topic were also paid in the doctoral thesis of Vittorio Paris, as in my previous didactical research at University of Bergamo, and the master thesis of Pezzoli, reissued in 2019. After the mentioned studies on the herringbone of Brunelleschi become now prominent, the reference to stereotomy and its theorems developed in France in the 17th and 18th centuries. On such study program, we get to design and make ready the physical model of a modular ashlar. In combination with other similar, it manifests a self-supporting behavior even in a dry displacement phase. Its employment let us design a vault surfaces with uniform and prefabricated element, showing equilateral triangular pattern. By the modular geometry of ashlar, by their uniformity and triangular mesh, we get an optimal discretization of constant curvature vault surfaces and more. Thickness and shapes are bound to stress resistance of the wall structure and to the required geometry for the bounding of the thrust surface. The reciprocal structural balance of assembled bricks is attained yet halfway during displacement of the distinct brick, making unneeded the work form and the temporary underpinning appliances. This last property encourages innovative development involving mechanical arm and drones. The research starts from an ancient narrative of stones, finding their equilibrium in the wonder of reason. From Brunelleschi dome to the mechanical arms of the modern-day robotics, where technology is performative of shapes and its social use. It is in this continuity of the eternal dialectic of the creative practice that our current research takes place.
La pratica ingegneristica e architettonica si attuano nell'inscindibile rapporto disciplinare che si lega sia al passato come
to fix that mirroring between modern and ancient, let's remember Heidegger's words, the great tradition advances toward us as future.
La grande tradizione viene verso di noi.
Okay, so we have time for just one very quick question. I don't see any question from the chat, so I will ask. I've seen that actually you were able to build 1/20th of an entire sphere, and of course, provided the global equilibrium of this triangular pattern. Can we say that we can build, let's say, cantilevering parts of a vault?
Posso rispondere in italiano?
Certo.
L'equilibrio che noi cerchiamo di realizzare con questi mattoni autoequilibranti, cioè self-balancing Ashler, è un equilibrio continuo che dovrebbe mettersi in continuità con l'idea di brunelleschiana della realizzazione di una volta senza l'uso di armature. Da qui diciamo il riferimento all'uso di bracci robotici o all'uso di droni nell'immagine di un futuro tecnologico, ma guardando appunto a questo autoequilibrio continuo che la volta realizza per un autocontrasto interno dovuto a delle ragioni che noi abbiamo verificato attraverso l'uso di software di elementi discreti, Tridec, che ha realizzato il mio collega e che oggi non può essere presente, Vittorio Paris, ma che ha fatto il dottorato su questa tematica.
Ok, quindi si riescono a realizzare tratti a sbalzo per la volta. Si reggono senza bisogno di supporto.
A sbalzo a piatta banda, cioè sono degli elementi incastrati che reggono i contrasti orizzontali, così come le spinapesce di questi mattoni verticali brunelleschiani che sono incastrati nel corso inferiore. Così corso su corso si realizza una struttura che si autoequilibria ma non cresce. Questa è la cosa che abbiamo verificato nelle volte del San Gallo, diciamo nei disegni stessi del San Gallo letti da questo punto di vista, e questo è un po' una novità. Per il resto il nostro studio è molto più elementare rispetto ai lavori che ha fatto Broccato, Parigi, però diciamo che ci piacerebbe verificare con loro, per esempio, come anche superfici negative, diceva Maurizio Broccato, non soltanto curve sferiche o positive, ma anche superfici negative o iperboliche possono essere realizzate con un mattone di questo genere. Insomma. Certo. Questa è la speranza di poter mettere a punto una verifica attraverso un'analisi limite che è quella derivata da Jack Hyman che abbiamo imparato da Santiago Huertas.
Ok, grazie. We are very short in time, so I will skip the translation, but And we can go to the next presentation, which is designed of pierced vault through form finding and digital fabrication by Riberi and Manuello.
Thank you.
Okay. Let's share the screen. Okay. Good morning, and thank you for the great opportunity. In these few minutes, I'm going to show you the main part of the study I have done with Professor Amedeo Manuello. Our goal was to show the great potential of masonry structures, particularly how masonry vaults can be also today an innovative architectural and engineering solution. The goal of increasing the openings for natural light and the importance to save material led the research to study pierced vaults typologies. We studied the form-finding process to design the geometry of pierced vaults starting from few governing parameters, such as the slenderness ratio and the holes pattern on the vault surface. Different funicular structures have been analyzed in order to compare them to identify the best shape together with its hole pattern configuration. Different form-finding processes have been evaluated. The multi-body rope approach proposed by Amedeo Manuello and the trust network analysis developed by Philip Bloch have been applied with the support of Rhino Vault, a free tool for Rhino. The design of the structure started with a squared geometry with a side of 16 meters. Different slenderness ratios have been considered, together with different holes pattern configurations. The TNA, starting from an initial planar hypothetical vault projection, found the equilibrium solution using static graphic principle, while the MRA based the principle of the form finding on the falling of masses connected by ropes in the time domain. Each geometry solution has been analyzed with a FE solver, LUSAS modeler and solver. A backlink analysis has been completed to study the global stability of each structure, and the first critical load multipliers have been recorded. To evaluate all the results of the analysis, a graphic representation have been realized. The first critical load multiplier values and the critical live load, that means that self-weight is not included, have been represented in function of the pierced area percentage. It has been noticed that for each hole pattern configuration, when the hole in the center of the vault is considered, the critical load multiplier is always higher than the holes pattern configuration with lower pierced area percentage. Also, the solution is always more stable if the holes are concentrated in the central part of the vaults. Moreover, the first critical load multiplier is always bigger than 1. That means that each structure designed with the TNA and MRA is able to carry at least its self-weight and additional vertical distributed loads, both symmetrical and anti-symmetrical. To validate the results of the analysis, one of the most pierced vaults designed has been chosen to be realized as a scaled prototype. With parametrical support of Grasshopper, the continuous surface of the vault has been divided into pieces. These pieces are the basis for the design of the brick for the vault fabrication. Their three-dimensional geometry has been found with Grasshopper. The bricks have been realized in mortar cement with a water-cement ratio of about 0.4. The formworks for each brick that have different shapes have been realized with 3D printing technique in PLA, a plastic material completely eco-friendly. Grasshopper was also used to design the falsework that had to support the bricks during the vault realization. That temporary structure has been realized with cardboard sheets placed on a plywood square panel, supported by 4 threaded bars that allow to control the height of the temporary structure. All the bricks have been placed on the upper surface of the falsework. At the end of construction, the spar has been removed. In this phase, the self-weight of the structure started to be carried. All the spar has been removed. Started to be carried out on the structure. Image correlation has been used to underloading. An incremental vertical load has been applied on the structure, and the deformations have been recorded. The DIC performed qualitative information of the structural behavior of the structure, and the deformation observed during the FE analysis were recognized in good agreement with the DIC displacements on strain measurements. So the DIC analysis can be used to extract measured parameters to recognize in advance the collapse condition of this kind of structures. Thanks for the attention.
Thank you, Federico. We have time for just one very quick question. So did you perform some loading test on this structure? I've seen in the preview material that you did it, but I didn't understand if it is loaded just vertically or also asymmetrically, maybe.
Yeah, we in the analysis, in the FE analysis, we did both symmetrical and anti-symmetrical analysis to secure of the structures. It has been designed also only for vertical loads, and the geometry of each structure we analyzed is designed on vertical loads. One of our future steps is to introduce horizontal loads such as seismic loads or wind load, because we want to understand the behavior of this structure if loaded with horizontal loads. So it's a future step of our study.
Okay, thank you very much.
Thanks.
So the next presentation is entitled Analysis of Masonry Walls through Simplified Micromodels by Alforno and co-workers. And I invite Alforno to present.
Yes, I'm here. Okay. Can you see my screen?
Yes.
Okay. So in my presentation, I will talk about masonry walls and the analysis with simplified micromodels. Okay, so masonry walls represent one of the most widespread structural elements in historic constructions. They can be built with different shapes and forms, but also with different construction techniques and different brick patterns. Great attention to bricklaying and the creation of the masonry apparatus can be found in the European technical literature, which has deeply dealt with the constructive phases of walls. This careful description of bricklaying probably highlights the desire to increase the strength of brick walls also through the building techniques. As a matter of fact, in Europe, from Roman times to modern ones, we can see that certain building techniques that were meant to be used in order to build without formwork are possibly used instead to strengthen the crown of the walls that were perceived by builders to be a weak point due to the opening of a crack in this part. So today we finally have the possibility to scientifically investigate these speculations found in the technical literature about brick pattern. To do so, discrete models are certainly more suitable than continuous ones to correctly describe the role of masonry apparatus. And among the different models, the proposed method of analysis implements a simplified micromodeling approach. The structure is schematized as a set of blocks connected by equivalent interfaces, representing the nonlinear behavior of mortar joints. The blocks are modeled as deformable elements with linear elastic behavior. And regarding the interfaces, the normal contact in compression is assumed as almost rigid through the definition of a normal stiffness Kn, and the tangential behavior is assumed to be purely frictional. The proposed approach has been validated through two experimental benchmarks, which are in-scale models of an arch and of a cross fault. Here you can see the second case study, which is a 1:5 scale model of a cross fault made of plastic blocks assembled with dry joints. Regarding the mechanical parameters, the elastic modulus E of the masonry assemblage was obtained by compression tests. As can be seen, the corresponding load displacement curves are nonlinear. And so therefore, 4 different values of E have been estimated and adopted in the analysis. Of the several experimental tests that have been performed on the scale model, 2 have been chosen to be simulated numerically, an opening test and a shear test. Here are the results of the opening test. The load displacement curves show a very good agreement between the experimental results and the numerical ones for different values of E. And the numerical and experimental collapse shapes show a surprising similarity. Regarding the shear tests, the numerical load displacement curves are in very good agreement with the experimental ones, and also the numerical collapse shapes perfectly reproduce the observed collapse mechanism. So with this validated procedure, we can apply it to a full-scale brick masonry vault to investigate the effect of brick pattern on their static behavior. So cross vault have been chosen, and they've been analyzed with 4 different patterns. Here we can see the model set up. In order to confine the web edges, vertical walls adjacent to the head arches were also modeled. And the vaults in this analysis are subjected to gravitational load only. The figure on the bottom left shows you the reaction forces that we monitored during the analysis. So the first analysis compares the vertical and pitched vaults. It can be observed that vertical brick laying does not allow for equilibrium in cross vaults, since the courses that are not directly in contact with the supports slide vertically. Conversely, pitched vaults are stable under self-weight only if head walls are present, otherwise a sliding mechanism occurs. A similar thing happens with the diagonal pattern. The outer part of the web edges cannot find equilibrium without the presence of confinement walls, but the rest of the structures appears to be stable. In the case of radial pattern, even though the vault is able to find equilibrium without head walls, the confinement due to the presence of walls contributes in stiffening the system, avoiding the out-of-plane deformation of the head arches. So in conclusion, this figure plots the reaction forces at the abutments and at the head walls for the 4 stable configurations. And we can see here that quite different values of thrust for different brick configurations, confirming a significant influence of the masonry apparatus, not only on the deformed shape, but also on the reaction forces at the abutments and at the head walls, allowing us to confirm some of the intuitions found in historical technical literature. Thank you.
Thank you, Marco. Thank you for the timing. Okay, so I have a question. So I find very interesting the effect that the head wall has on pierced vault and on vault having diagonal and radial patterns. And with this effect, of course, is not present in what you call the vertical cross vault.
Mm-hmm.
Are you planning to do some parametric analysis in which you can study the effect of brick and the interface material parameters on this effect, on the effect of the head walls, I mean?
Oh, okay. So the possible parametric analysis we could do on that vault is regarding the friction coefficient. Increasing the friction coefficient may stabilize the central part that is sliding. We are not planning to do that, but we could do it. We could do it.
But do you expect it has some effects?
No, we expect that the central part will still go down because it's the greatest part of the structure. So it has there are strong shear forces, great shear forces along the joints of the arches that are stable and the ones that slide down. So possibly that is not a stable configuration. As a matter of fact, we didn't find any information regarding this pattern on European technical literature, and we didn't find vaults built with that with that pattern. The same, we found examples and built architecture with the other patterns, but that pattern is not present. This is probably due to the fact that it's not a stable configuration.
Okay. So, and I've also seen that from experimental results, you can obtain 4 values for the elastic modulus, but I didn't understand well how you apply these to the model, since you say it is the result of an interaction between the mortar and blocks, but then you in the model you model separately the two elements.
See, okay, so, the modulus, the elastic modulus of that assemblage. So the elastic modulus was of the assemblage of 6 blocks that were compressed, and the blocks were assembled with dry joints, because that kind of structure was built with dry joints. Okay, so we did several analyses with the 4 different values of elastic modulus we found, and in order to see the influence of elastic modulus of the assemblage on the collapse mechanism. The collapse mechanism is the same. The ultimate displacement changes. And we did that parametric analysis because we saw that, maybe I can go back and show you, but because we saw that the ultimate displacement is overestimated in respect with the experimental ones. And so we did that parametric analysis to see if elastic modulus does have an influence. So yes, it does. But the overestimation of this test is probably due also to some imperfections in the experimental model that we saw during the experimental test that were not accounted for in the numerical model.
Okay, thank you.
Yeah, thank you.
So let's go to the next talk, which is by Roberto Spagnuolo. The title is Out-of-Plane Local Mechanism Analysis with Finite Element Method. He asked us to show his video presentation, so I asked Andrea to help me with that.
Yes, do you see it?
Yes.
Okay, I will play it.
Shall I compare to a summer day? I'm not speaking about the weather, nor I am quoting Shakespeare, Sonnet 18. I'm quoting Mr. Turing as we will speak about computer. In the speaking about computer, I will wish to introduce to you my personal PowerPoint. Please come PowerPoint. He is my personal PowerPoint. His name is Johnny PowerPoint. Let's go. Are you ready? Okay. Many important structures were designed and built in the past without the use of computer, but the cost and the necessary for design were greater than nowadays. I was an assistant of Sergio Musumeci, so I know the Basento Bridge history very well. The Basento Bridge was born from the genius mind, and it required a costly model. This is, please show me the slide. This is the first neoprene little model that has been now unfortunately lost. And this one, the second piece, the other slide, is the expensive model in microconcrete. The bridge was recently, you can change the slide. The bridge was the subject of a recent paper where there is a contribution mine for the FEMP model. It shows the useful stress distribution that is a prerequisite for minimum weight. Unfortunately, nowadays is a certain reluctance toward computational mechanics in everyday design practice. We often see collection solution according to the method of the Roman Empire, divide et impera. This is an example or recommendation about autoplane mechanism analysis. There is not a general solution. In fact, the next one, please. In fact, simple spreadsheets are often used for this simple algebraic model. This is an example. In my work, I will illustrate a topic that you often encounter in everyday design of masonry. That is the analysis of autoplane mechanism in masonry structures. This problem can be tackled with the truss line obtained through the firm analysis. Which slide? No, let me see which slide is it. Okay, that's correct. In order to solve this problem, we used a layered degenerated shell element with 10 nodes with a no-tension material and a smaller crack, rotating crack. To show this method, we applied it to the analysis of an arch. This shows the arch. No, the arch. This is the arch. This one. This is a truss line the arch. Now we see PowerPoint. Let us see the next slide. The eccentricity of the truss line in color. This is through a linear analysis. In the next one, we can see the difference with the results of a nonlinear analysis with the no-tension material. The reason is clearly shown in the next image. PowerPoint, please. And now, this is the, are you in the correct slide, PowerPoint? No. This is the truss line in a dome. In the dome, there is an analysis problem due to the vertical cracks. We have dragged the stiffness matrix to avoid this problem. And now, finally, the next one, please. And now, finally, we arrive to the masonry corner, which is the most tedious problem to solve manually. And this, I think this is the last one. No. This is also, and now, this is the computational firm solution. It is general. The shape of part of masonry in which the truss line is out of the surfaces, in red, is satisfactory. And the numerical results here not shown, also satisfactory. Thank you for your attention. I forgot. My name is Roberto Spagnolo. Softy, Rome.
Okay. Thank you, Andrea. So I have a question for Roberto, and the question is, since I like a lot the way he's plotting the truss line or the truss surface on the model, and I wish to know how this tool will be available on the commercial version of Nolian All-in-One, if it is not already there.
Yes, I know that you. Do you hear me? Because
yes, I can hear you.
I know that you are a Nolian user, I think, or not.
What? I'm not?
Are you an Nolian user?
Of course I am.
You can find the representation, the eccentricity of the truss line.
Ah, okay. I didn't know that. Thank you. So I already have it.
No, it's very amusing. I have many satisfaction from this.
Okay,
It's
great.
Not a great invention. It is an old invention. But the solution to this kind of finite element is very satisfactory, I think. You will use it and tell me your opinion.
Okay, and also Stefano has a Stefano wants to give Roberto Spagnolo the best video awards, of course, for the intervention of his Johnny PowerPoint.
Thank you. But the most difficult was enroll the seagull. You have heard the seagull.
Okay. Yes.
The seagull in the exact moment is not easy.
Yes.
Thank you. You are very nice with me.
Okay. Then we have a question from Francesco Tornabene. Francesco.
For me?
Yes.
Yes.
Can you hear me?
Not difficult, please.
No, no.
Very easy, very easy.
Don't worry. It's an interesting presentation. I want to know if you can trace the truss line for each kind of dome. So independent from the shape. So you can find the truss line for each kind of dome, or only for some types of dome, some type of domes.
No, as it is a finite element approach, there is no limit on the shape. The problem in the dome is that you have vertical cracks. So the element became unstable. The matrix is not positive definite. So we have dragged the matrix for this kind of, but I think that this problem can be afforded with general methods if you want. No, there is not a limit of shape.
Thank you very much.
Thank you to you.
Okay, we have more comments from the chat regarding your assistant, Roberto.
I will refer.
Okay.
Thank you very much. Also from
so
John.
We are short of time. I will give the comments you privately. So next presentation is by Ceravolo, Lenticchia, and Oliva, and regards design schemes and some observed structural behaviors. Experiences learned from testing on a pre-stressed concrete pavilion designed by Morandi.
Yes, good morning to anyone. Thank you, Francesco, for the introduction. I hope you can hear me.
Yes, yes.
Okay, the present work with Professor Ceravolo and Dr. Erika Lenticchia is titled Design Schemes and Observed Structural Behaviors, Experiences Learned from Testing on a Pre-Stressed Concrete Pavilion Designed by Morandi. This contribution is part of the fairly current research about modern architectural heritage. When dealing with modern architectural heritage, there are many issues connected to its preservation or rehabilitation. First, lack of recognition. Second, the continuous experimentation of new construction techniques and materials by the designers of the period. Moreover, these structures were generally built without taking into account seismic action, but only static configurations. A part of this heritage is represented by structures built with pre-stressed concrete system. This technique is very sensitive to natural deterioration and to excessive environmental attacks and require in-depth analysis. This work aims to present a valid methodology for the diagnosis of 20th century architectural heritage, reporting some significant results obtained from the investigation conducted on an iconic pre-stressed structure built by Riccardo Morandi in the late 50s, namely Pavilion 5 of Turin Exhibition Center, focusing in particular on constructive and structural aspects. The structure was conceived with a post-tensioning concrete system patented by Morandi and is characterized by a complex spatial design. A test campaign was conducted recently on the pavilion, which produced a calibrated FE model. For the static behavior, also direct reference is made to Morandi's calculation schemes in the original design documents. The final scope of this research is to evaluate the structural and seismic behavior of the pavilion in order to better understand and preserve Morandi's architecture. Pavilion 5 was built in 1959, commissioned by Società Torino Esposizioni. The pavilion consists of a single wide space, 69 meters in width and 151 meters in length, located 8 meters below ground level. The scheme adopted by Morandi for the pavilion is the so-called balanced B scheme, used by the designer for the construction of some bridges in Italy. The structural conception consists in post-tensioned beams on two inclined supports with two cantilevering side spans anchored by post-tensioning tendons at their end, exerting a balancing effect on the main span bending moment. The cantilever provided a first reduction of bending moment in the span. In addition, cantilever efficacy effect increased due to a vertical concentrated load at the cantilever ends. This concentrated load applied by the tensioning of the tendons embedded in these short strut beams, this element, allow to balance the maximum bending moment here in the midspan and the minimum bending moment here in order to reach the most efficiency structural solution. Here we can see the main elements of pavilion in the figure on the left, and on the right we can see a plan view with the main beams, the ribs. These ribs are branched out to obtain a spatial structure that provide high overall rigidity and an efficient constant to the stability of the very thin webs of the ribs. The structure is divided into three main bodies by means of two expansion joints, which cross the roof and the external walls, and whose behavior was uncertain. The preliminary assessments began with the creation of a 3D geometric model, which was transferred to a FE code to perform a structural assessment. A model analysis with seismic design spectra was executed. In the analysis, particular attention on some identified critical elements was paid. In the preliminary seismic assessment, the main uncertainties of the structure concerned the effective functioning of the joints, modeled as shell elements with a fictitious thickness. Since it was difficult to a priori predict the contribution of the expansion joint to the structural behavior of the pavilion, as a first attempt, an elastic modulus was assigned to the joints to guarantee an overall behavior of the pavilion, and we can see it in this model shape. The assessment conducted for the selected elements provided the following information. The structural verification under bending moment and axial force of the longer strut beams, these, are not satisfied. And second, non-sufficient reinforcement for the shear structural calculation are present in the shorter strut beams, this element. An experimental campaign was conducted in 2019. Mechanical tests were executed to evaluate the compressive strength of the different elements of the structures, and the results of these tests show that the structure is made of concrete with reasonably high compressive strength. The investigation also verified the position and the state of post-tensioning cables through scarification of some ribs. We can see it. The latest investigations have provided the useful in diagnosis the important state of corrosion of cables, as well as grouting defects. The program also included static tests, we can see it in the figure on the right, on two different ribs to assess the bearing capacity of the structure under characteristic variable actions. Dynamic tests were executed, moreover, to identify the model characteristics. These tests were carried out with natural excitation, which represent a non-invasive investigation techniques to avoid damaging the structure. The acquisition system was composed of 20 monoaxial piezoelectric accelerometers positioned on different elements. And we can see that overall 2 setups were designed. The dynamic characteristics of the pavilion were identified, and the result of the experimental tests were then used to corroborate the initial FE model. An accurate analysis of the model shapes confirmed the effectiveness of the 2 joints in the transverse direction. Consequently, the overall dynamic is characterized by the interaction between 3 portions. Therefore, the elastic modulus of the joints was reduced by 1 order of magnitude. Being the horizontal response related to the rigid roof, the main defense line against the earthquake acting along the longitudinal axis lies in the shortest strut beams, and we can see it a shape mode in longitudinal direction. The presence of effective joints in the roof constitutes an important factor of vulnerability due to the possible pounding between the 3 distinct bodies, as we can see here. For what concerns the static assessment for Morandi's pavilion, the main static problem is represented by the conditions concerning the corrosion of the post-tensioning cables in the main ribs, in consideration of the very thin thickness of the webs and of the possible grouting defects, typical these defects of the construction technologies and control system adopted at that time. The corrosion of steel both in the ribs and the shortest strut beams are confirmed as the main obstacle to the preservation and reuse of this type of structure. To conclude, this contribution illustrates the important role of a multidisciplinary approach used to analyze 20th century architectural heritage for a correct diagnosis of the structural health. In this study, the vulnerability aspect of the structure conceived by Morandi, both from the durability of the pre-stressed concrete elements and the seismic points of view, was investigated. The post-tensioned system is known to be very sensitive to corrosion phenomena and requires in-depth assessments to appropriately read the structural conception of the building. The main problems that threaten the structural safety of the pavilion are summarized in these figures below. Thank you for attention.
Thank you, Valerio. And so I have a question. Is this building actually abandoned now, right?
Yes.
It's not in use.
So it's not.
Yes,
it's correct.
Yes,
it's correct. It's not in use. It's only used for a temporary event. Not is used permanent. So it's okay. Correct. Yeah.
Is someone thinking of retrofitting the damaged structural parts? And what is your idea about how to retrofit this part while preserving the historical and artistic value of this structure?
Yes, there are some projects for the future of this structure, and this project want retrofitting this pavilion with a method that respect the historical value, as you said, and one of this project is correct from a philological point of view. That is a pension of the principal elements of these structures to another steel truss structures. Another thing is that these structures have much robustness due to the intersection between the different ribs, and this can help in the structural safety of the structure.
Okay, thank you. And also Amedeo has a question. Amedeo, please.
Yes, I know that there is not more time, but a curiosity. Do you know which is the imminent future of this structure in terms of the plan of the city or the owner? they wanted to reuse in which manner?
Yes, I don't think that it can be reused in imminent period. I think that was necessary some interventions for guarantee structural safety. Most of all for that concern the as I told, the problem of grouting the fat inside the tendons, as we can see here with an endoscopic survey. There is a problem that when corrosion increase in the principal beam, we can have a reduction of resistant bending moment. This is a section of these beams. And this is first problem that can affect the structural safety. The second problem is concern the pre-stressing inside the shorter strut beams, because the structural conception by Morandi can reduce the bending moment in the mid-span by means this downward force. So when these elements, steel element, have corrosion, we have an increase of bending moment in the span. This is the static problem. For what concerns the seismic problems, as we can say, we have, as I can say, we have the problem of pounding. That is another important problem. So probably in any retrofitting intervent are necessary then some shock transmitter device. And so
thank you very much.
I think that was necessary time. Yeah.
Yeah.
Thank you.
We need much more time to talk about this.
Thank you very much, Valerio.
Thank you.
Thank you. So we have the last presentation by Abruzzese, Tiero and Micheletti. And the title is Permanent Monitoring of Thin Structures, and is presenting Abruzzese.
Yes, good morning, everybody. Thank you for this occasion to discuss, even being everyone at home or somewhere else. It's clear what, can you see me?
Yes.
Yes.
Yeah, okay. So this presentation is inside of a larger project. It's called Money to be Safe project. And then the main idea is to make the monitoring system of the structure. So in this case, we are talking about thin structures, but of course our presentation can be extended, our work can be extended also to other situations. The main activity we have is to prepare some device, like we can say homemade embedded sensors. So we put in the beams or somewhere else in the shell or other kind of concrete structure, main concrete structure, but of course can be also extended to steel structure. And for instance, we have here some plates. This is the concrete plate reinforced, carbon fiber net reinforced. And here on the other side, we have also masonry, brick masonry panel. We put on the test with some typical bending test or shear stress. And this kind of sensor just as skin sensors. And all these kind of sensors are controlled by small like Arduino-like system. Like here we see a little box we prepare and we test it. And this is a very simple example of comparison between one sensors controlled by our small box and another sensors controlled by very expensive machine. I mean more than 50 times more expensive. And you can see, except the last part is related to the crash moment, collapse moment, all the rest is pretty in good agreement. So this is another test related with the shear test from panel. You can see here our small device. Devices are deformation devices, and instead of to use accelerometers that give you just an indirect information about the stress, we are using deformation can give some direct information about the stress. So imagine, for instance, a shell with a double curvature and n phi and theta stress. We need, of course, some model to solve this structural problem. But if we imagine to put in one point some kind of deformation sensors like this one, we can have a sort of skin effect. It means membrane behavior, or some other inner embedded sensors can give you some information about the flexural behavior. Now there are some kind of piezo actuators or sensors. Actuators can be controlled by electricity, but can be also reverse. In this case, we are using the reverse way, so as sensors, and then they can give you information about the deformation. We can have some information about the rotation, the curvature, the variation of curvature, and it means also stress. Just imagine some very complicated shell like this one. We are talking here about this as a Aero Sarin and wonderful TWA terminal in New York from 1962. You can see this is not so easy to make some calculation. We are talking about double curvature shell, and what they are doing now, they are using a very complicated system like a Rhino, grasshopper, other kind of assistant design program, and then you can have some idea. But always you need to check your design with some control. So our idea is that if you have some kind of structure, very complicated structure like this one, this is a tennis center in Hangzhou in China, 80,000 people capacity. This is made by grasshopper and other system. They call also a RIMO. RIMO means a rhinoceros plus model, or some other kind of program that control and help you to control the shape and also the structure. You need also to make monitoring. Monitoring is very cheap, and nowadays is very simple to organize, but we need to use it, because in that case you can have a sort of very good control of the structure, like you have in your car. In your car you can control everything, your tires, your temperature, everything. Why we are civil engineer, we cannot control our pretty good and wonderful shape made by some crazy architect? Why not? Thank you very much.
Thank you, Professor Abruzzese. And I see that there is a question from Amedeo again.
Where is Amedeo?
Yes, I'm here.
Yes, Amedeo, I see you. Ciao, Amedeo.
Nice to meet you. Thank you very much for the nice presentation, Professor. I want to ask if it's possible to use also acoustic emission sensors that are piezoelectric sensor positioned on the surface of the structure. In this case, you can also localize by triangulation the source of the image.
Yes, look, this kind of system are being used pretty much mostly on the suspension bridge on main cable, and they help you to make this localization. So on. I can never say don't use this or use that. I will use everything you can. Now it's very cheap. It's not very expensive. Okay, acoustic emission is not so efficient in the sense of you need to make a very high frequency recording system to get this information. So you need always to have your ear there, but you cannot do that. So it's related with the number of sample numbers that you get from your system. but in that case, it's pretty useful. So, but if you put together deformation sensors and also acoustic sensors and also dynamic sensors, it means accelerometers, in all this system can give you the main idea, and then you can also make a model that in a real time you can give the real effect of the situation. And most important, you can also record all this information in one database, and even after event, after earthquake, after the shock, after the crash, after something, you can have the information about what happened before. It's like a black box. You can have always somewhere, and then can give you some information. I don't know if it's clear what I said.
Yes, thank you so much for your answer.
So thank you. I also have I want to ask you a comment about the economy of permanent monitoring. What are the costs and savings?
The cost, of course, will range in the sense you can have a very nice fur, or you can have just like a fake fur, or just like a wool, or you can have cashmere. It doesn't matter. It's important you have some sensors. In what we are testing now, it's very cheap in our laboratory. We are spending like I can say, compared with the past, 100 less than the past. It means if you are going to have a very good monitoring system, you can going to spend 1 or 2%, no more than that, of total cost of the structure.
Okay, thank you. We have also a question by Stefano Gabriele.
One by one, you are getting interested. Who is there?
Thank you.
Yes,
I'm here.
Oh, Stefano.
Thank you for your presentation.
Gabriele.
Yeah. Yeah, Stefano is the first name.
Yeah, sorry.
No, it's okay. So I would like to ask, because for permanent monitoring, okay, costs could be important, but for this, in my view, much more important is the precision that you can request it to the monitoring, and also the ratio, how much your sensor is affected by noise that you have in the surround or in the environment. At the stage of your development, how is the situation about the precision and the ratio between sensitivity and noise of the sensors?
Yeah, this is a very interesting question. I can come out with one example. If you're working with wires that are pretty protected, and now we can do that. It's not so difficult. We can come out. We can have some very good information with very low noise, and we test in the laboratory with a lot of environmental noise, electronic noise, because in laboratory we have a lot of noise. I can measure with a special kind of instrument a lot of noise, but it affects more electronic device like accelerometers or other kind of things. But these kind of things related with deformation, the cables can protect the signal. And on the other side, there is the communication. The communication is very important because the communication now is Wi-Fi or Bluetooth, or anyway is wireless. This kind of, and that's another kind of field to investigate and discover. But even in this moment, we can be pretty much, we can rely pretty much on this kind of architecture, because even without wait for the 5G, we can have I can say that we are going to have a pretty good structure. I mean, architecture for the device we are going to use for the structure.
Thank you.
Okay, thank you very much, Professor Abruzzese. I wish to thank all presenters of this session, especially the keynote lectures, Professor Brocato. And let's see you again at 2 p.m. So people connected to the Zoom meeting can remain on Zoom, while people following the workshop on YouTube, they will be warned when the new live stream will be online. Thank you, everyone.
Can I add something? So because
Yes.
I will be chairing the next session. I will start connecting with to check if all the authors will be present and all the presenters will be present 50 minutes before 2 p.m.
Okay. So see you later. Thank you, everyone.
Anyway, the connection
will be on. So if you can just close your camera and then have lunch.
Or talk, and you are welcome to use this as a chat and exchange and everything.
Okay. See you later.
Okay, thank you very much.
See you later.
Have a nice lunch.
Bye bye.